The race to produce clean hydrogen has always been defined by one big question. How do we make it cheap enough and clean enough to replace fossil fuels? For years, the spotlight has been on electrolyzers, those sleek metallic devices that split water into hydrogen and oxygen using renewable power. They've dominated the conversation about the green hydrogen revolution, but a new contender has quietly emerged from beneath the Earth's surface, challenging the very assumption that hydrogen has to be manufactured at all. What if, instead of making hydrogen, we could mine it directly from the planet itself? That's the idea behind an emerging frontier known as geologic or natural hydrogen, and one company claims it can do exactly that. Meet Decahydron, a startup that believes hydrogen is already being produced naturally by the Earth's own chemistry, and that with the right technology, we can tap into those underground sources to fuel a carbon-negative future. While most of the world is still focused on scaling renewable power and electrolyzers, Decahydron is looking downward, deep into the mineral layers of ultramafic rock formations that have been reacting with water for millions of years. These rocks, rich in magnesium and iron, engage in a process called serpentinization. When groundwater seeps through them, the minerals react, splitting water molecules and releasing molecular hydrogen as a byproduct. It's a quiet, continuous reaction happening all around the world, mostly unnoticed. And for Decahydron, it could be the key to unlocking a vast new source of clean, low-cost hydrogen. What makes Decahydron's approach radical isn't just that they're harvesting hydrogen from rocks. It's that they've found a way to stimulate and accelerate this natural process. Their method involves injecting carbon dioxide into specific rock layers where hydrogen is already being generated. The CO2 reacts with the minerals to form solid carbonates, permanently locking away the carbon while simultaneously displacing hydrogen, which can then be captured and purified. In other words, one geological system performs two jobs. It produces hydrogen and stores carbon, turning a natural geochemical process into a man-made energy solution that could potentially operate at gigaton scale. That's a bold vision, and it stands in stark contrast to the traditional green hydrogen approach. With electrolysis, the goal is to use renewable electricity, mostly from solar or wind, to split purified water. The challenge is that both of those inputs, electricity and water, come with costs and constraints. Electrolyzers are expensive, often running into the millions of dollars per megawatt. They also require ultra-pure deionized water, something scarce in arid regions where renewable potential is highest. Add to that the high energy consumption, roughly 50 to 60 kilowatt hours of electricity per kilogram of hydrogen, and you start to see why the current cost of green hydrogen remains stubbornly high, often around $5 to $7 per kilogram in most markets. Even with declining renewable prices and improving electrolyzer efficiency, reaching the long-sought $2 per kilogram target has been difficult. Decahydron, however, claims it can beat that cost and even go below it. By removing the need for electrolyzers and renewable electricity, they cut out two of the biggest capital and operating cost drivers in the hydrogen supply chain. Their process, which relies primarily on geological reactions and CO2 injection, consumes minimal electricity and virtually no processed water. If proven at scale, that could bring production costs to below $1 per kilogram, a figure that would completely rewrite the economics of hydrogen. And because the process actually locks away CO2 in solid mineral form, the resulting hydrogen could even be carbon negative. That's a claim few other hydrogen pathways can make. But before we get ahead of ourselves, it's important to understand the state of this new field. Natural hydrogen, sometimes called white hydrogen, is still in its infancy. While traces of hydrogen have been found in many parts of the world, France, Australia, the US, Mali, and Russia, few commercial projects exist yet. The science is proven, but the scalability is not. Hydrogen molecules are small and diffuse easily through rock pores, which makes exploration and capture challenging. The idea of hydrogen wells, similar to oil wells, is still largely experimental, but early exploration results are promising. In Mali, a village called Burakebugu has been running on naturally produced hydrogen for years, providing a glimpse of what's possible. Decahydron's ambition is to take that concept global, with the added advantage of CO2 mineralization. The dual reaction at the heart of Decahydron's system, hydrogen generation and carbon mineralization, relies on one of Earth's most powerful chemical processes. When CO2 comes into contact with magnesium or calcium-rich rocks, it reacts to form solid carbonates like magnesite or calcite. These minerals are stable over geological timescales, meaning the carbon is permanently stored, not just sequestered temporarily. By injecting CO2 into these reactive rocks, Decahydron effectively kills two birds with one stone. It displaces hydrogen that's trapped within the rock matrix, and it transforms the CO2 into rock. It's a self-reinforcing loop that could, at least in theory, generate clean hydrogen while permanently removing carbon from the atmosphere. For investors and developers, the potential implications are enormous. Imagine a hydrogen project that doesn't need to wait for electrolyzers or gigawatts of solar panels to be installed. Instead, it could be developed wherever the right geology exists, similar to how geothermal projects are sited today. The infrastructure footprint would be smaller, the energy input lower, and the life cycle carbon balance potentially better than zero. Moreover, this approach could complement existing carbon capture and storage efforts, turning what is usually a costly process of burying CO2 underground into a profitable one that simultaneously produces a valuable fuel. Of course, the path from scientific possibility to commercial reality is rarely straightforward. There are significant technical, economic, and regulatory hurdles that Decahydron and others in the geologic hydrogen space must overcome. Subsurface hydrogen generation rates must be proven stable and predictable. Extraction wells must prevent leaks and contamination. CO2 injection must be carefully managed to avoid overpressure or unwanted chemical side reactions. And regulators will need to adapt frameworks designed for oil and gas or CO2 storage to accommodate this new kind of dual-purpose project. Yet, these are precisely the kinds of challenges that innovative startups exist to solve. When comparing Decahydron's vision to green hydrogen, the contrast becomes even more striking. Green hydrogen depends on scaling industrial equipment, electrolyzers, compressors, pipelines, through mass manufacturing and policy support. The path to cost reduction is largely technological and economic. Build bigger factories, improve efficiency, and lower the price of renewable energy. Geologic hydrogen, by contrast, follows a geological logic. Find the right rocks, optimize the injection chemistry, and let nature do most of the work. In a sense, Decahydron's approach shifts the hydrogen problem from engineering to geology, a paradigm shift reminiscent of how geothermal energy evolved from curiosity to infrastructure. Another major difference lies in scalability. Electrolysis can, in principle, be built anywhere there's electricity and water. But geologic hydrogen is tied to specific rock formations. The good news is that ultramafic rocks, the ones best suited for serpentinization and mineral carbonation, are widely distributed across the planet. From the Oman ophiolite belt to parts of the US Midwest, from Norway's peridotite massifs to Australia's Pilbara region, there are hundreds of potential sites where hydrogen could be generated naturally and extracted. What remains to be proven is whether these resources can sustain commercial-scale production over time. If they can, the implications go far beyond cheaper hydrogen. This could redefine how we think about the hydrogen economy altogether. Today, most hydrogen is produced from natural gas through steam methane reforming, releasing large amounts of CO2 in the process. Even so-called blue hydrogen, which attempts to capture that CO2, still relies on fossil feedstocks. Green hydrogen via electrolysis eliminates those emissions, but struggles with cost and scalability. Geologic hydrogen, on the other hand, offers a third way, a form of hydrogen that comes directly from the Earth, with no fossil inputs and potentially negative carbon intensity. If proven viable, it could make the term green hydrogen look outdated, replaced by something even cleaner: Earth hydrogen. From an economic standpoint, Decahydron's model also aligns with a growing appetite for carbon removal technologies. Governments and corporations are increasingly investing in permanent carbon storage solutions, from direct air capture to mineralization projects. If a single process can both generate hydrogen and sequester carbon, it effectively doubles the incentive structure. earning revenue from hydrogen sales while qualifying for carbon credits or removal payments. That financial synergy could help geologic hydrogen scale faster than many expect, especially in markets where carbon pricing and clean fuel incentives converge. Technologically, Decahydron's system could evolve alongside the existing energy industry. The same subsurface engineering expertise used in oil and gas, drilling, reservoir management, seismic mapping, can be adapted for hydrogen and CO2 mineralization. This opens a pathway for traditional energy companies to pivot toward a cleaner business model without abandoning their skill sets. It also creates a workforce transition story where geologists, drilling engineers, and subsurface scientists find new purpose in fueling the hydrogen age instead of the hydrocarbon era. Still, the biggest unknown is time. How long before geologic hydrogen can move from pilot test to meaningful production? If history is any guide, new energy paradigms take years, sometimes decades, to mature. But the current pace of innovation is faster than ever. Countries like France, Australia, and the US are already mapping natural hydrogen potential and supporting early exploration. In the US, this fits neatly within the broader framework of the Inflation Reduction Act, which rewards clean hydrogen production based on carbon intensity rather than specific technology. If Decahydron's process can demonstrate a low or negative carbon score, it could qualify for the same federal incentives as green hydrogen producers, unlocking significant capital. At a deeper level, though, what makes this story fascinating is how it reframes our relationship with nature. For years, the clean energy movement has focused on mastering technology: solar panels, wind turbines, batteries, electrolyzers. Decahydron's approach suggests that perhaps nature itself already holds part of the solution, and our role is simply to understand and accelerate it responsibly. Instead of forcing energy from matter, we could be amplifying processes that the Earth has been running since long before humans arrived. It's a humbling and hopeful perspective that bridges geology, chemistry, and sustainability into one elegant system. If geologic hydrogen proves scalable, it won't necessarily replace green hydrogen. It might complement it. Electrolysis will remain essential in regions rich in renewables and poor in geological potential. Geologic hydrogen could thrive in places with the right rocks but limited power infrastructure. Together, they could form a diversified, resilient hydrogen supply chain, one that's not dependent on a single technology but adaptive to local conditions. And that, ultimately, could be the key to achieving global hydrogen adoption faster than any single pathway could manage on its own. In the end, whether hydrogen is made in a factory or mined from the earth, what matters is how quickly and sustainably it can replace fossil fuels. Decahydron's vision challenges us to think differently, to look below our feet for answers rather than only to the sky for sunlight. If successful, their model could open a new chapter in energy history, one where the planet itself becomes both the power plant and the carbon sink. It's a future that combines science, sustainability, and imagination, and one that might just redefine what we mean when we say green hydrogen. At h2hub.renewable.com, you can explore how innovators like Decahydron are reshaping the hydrogen landscape. Our Hydrogen Project Starter Kit gives you the feasibility checklists, financial models, permitting roadmaps, and risk registers you need to navigate this new era of clean hydrogen. Whether you're building an electrolyzer project or exploring next-generation methods like geologic hydrogen, visit https://h2hub.renewable.com to learn how to plan, price, and execute your hydrogen project with confidence, backed by real-world tools and templates designed for developers, consultants, and investors.